Hello, hello. Hello, Lila. Hello, sorry, I let everybody in. Sorry, it's a little early. Well, it was, whatever. Hello, Lila. Hello, Michael. Okay, see you. Good to see you. All right. Love the wave. It's all about waves in this class. Okay, and there's chat, people going on. Hello, good afternoon, Danielle. Good afternoon, Luis. Good after. Hello, Jadith. Hello, Nico. Okay. Oh, and there's Joyce. Okay. Yeah. Yes. I'm always, I'm always freshly, pleasantly reminded that this class is a high video class. I really appreciate that. Joyce and Michael and Lila. And okay. And Samaya. Hello. Good afternoon. Okay. Um, okay. So let's do some physics. We're gonna go in a way. It's my favorite topic. We're starting now. I mean, you thought I liked the other topics. You can't even believe it. But because we didn't have class Wednesday, because I am falling a little bit, well, because I have fallen a lot behind. Okay. I'm gonna bear with me for a second. Sorry, bear with me for a second. Hold on. Hold on. Sorry. Yes. Okay. Yes, you are bearing with me, and I appreciate it. I'm still here. I'm looking at something because it might affect what I'm about to say or what I'm about to do. Um, I should probably pause the record. Oh, oh no, yes. Okay. Okay. So I owe you guys some things in addition to the exams, but I'm looking quickly. Hold on. Okay. Okay. Wow. Okay. Wow. All right. Let me say, I'm a little bit behind, and when I say little, I mean a lot. Um, what I'm looking at right now in real time, just because I don't, because I am looking at what you wrote about the videos that you watched last Wednesday. I'm looking at what you wrote right now because it's really thorough what you wrote. I mean, where I asked you to say, um, one thing that you did understand and one thing that you didn't understand. And you haven't gotten the points for that. You will get every one of you who did it will get all the points, and you'll probably get them in 5 minutes from now. But ideally, I had wanted to like write directly on them, but I am reading them right now, and they're really thorough and thoughtful on your part, and they're really helpful to me as to how we're going to do this class. Okay. Because I'll talk to you while I'm looking at this. Where we need to go now in this class, as I say, my favorite topic is this concept of flux, electrostatic flux, the equation that's written on the board the definition that's written on the board right here is the definition of electrostatic flux. That's where the class has to go right like now. But but yes, indeed, in order to study and solve problems with electrostatic flux, yes, you need to have some comfort or some background in field lines. And I'm looking at what you all wrote about. And so in theory, you saw the videos about these field lines. So it is true that I don't want to waste your time. I don't want to do those classes over from scratch and have you do the same classes twice. But looking at these questions of yours or these comments of yours, it does appear that the field lines are not 100% clear to you. So, all right, so this is what we're going to do. Okay, this is what we're going to do. I mean, because your comments are really good, and I want you to get the points for your comments instead of holding you up and like putting individual responses to each one of your questions on these. And again, I'm talking about your responses to the videos from last week. I think it's better if I like try to give you responses right here in the class. Draw the electrons so they represent the same. Okay. All right. So here's what we're going to do. I'm going to need your help to help me help you. Um, I Right now I'm going to try to wait, I'm looking at, and yes, right, we don't meet this Wednesday. Yeah, that this time I knew that. Or did I mention something about this? Right, no, right, we do not meet this Wednesday. That much I do know. Right. So hence I'm a little concerned about time. A little. Um, um, so what I'm going to try to do now, having just looked, I have two things I'm going to ask your help with. Number one, all of you who made comments about the videos as asked, I want to make sure you get your points back before this class is even over. I mean, I'm not going to put feedback on them. I'm going to try to do the feedback like right here through the class. So just remind me if it gets to like 4 o'clock, just remind me to take 5 minutes to pause and make sure if I haven't done it by then to make sure you get your points back for it. But yes, Jadith, that's right. This Wednesday is a Friday schedule. So like you do have John Jay, you just don't have me. What second prize? I don't know. So what I want to do now, so first of all, yes, I want you to get your points. Thank you, because it really your feedback was really thorough. And so thorough that it's telling me that I should not just skip straight to flux yet. I should try to clarify these field lines. So that's what I'm going to do right now. But you really need to have I'm trying to cater to what you wrote in the video feedback. But if I get bogged down, politely tell me, please, in direct chat or whatever. If I'm getting bogged down in something that I already spent a million years on the video, let me know. That's number one. Number two, the goal of anything I say about field lines here, the goal is to get to this equation right here on the board. Now, anything about that, it seems like from your feedback, frankly, I didn't realize, but it seems like from your feedback to the videos, it seems like at least in one of the videos, I did actually mention that equation. Could you verify or deny in the chat? Like, did that equation actually come up in one of the videos? Yes. Yes. Okay. All right. So that's good. That I will realize, like if that is part of your, because some people wrote like they found that confusing. If you found that confusing, don't worry. I will more or less start from scratch on that. Well, I will, because like, yes, that's what it's all about. We're going to be spending a while on that equation. So don't worry if you miss that in the videos. But here's a part that I'll what I'm going to do is try to summarize the issue of field lines in general. What I'm not going to do is rewrite all the rules for writing them and reading them. Like the rules themselves are in the videos. I'm going to try to like give big picture here, like what the rules like end up doing for us. Okay. So again, you got to tell me in the chat if I'm going too fast or too slow, or if I'm like on the wrong, or if I'm like to the left of wherever you want me to be. So quick summary of field lines. First of all, like I don't know why that was. Okay. First of all, one question that came up in the in your video portal, one question that came up like twice at least was I someone said I don't understand like the difference between field lines and vectors, or how do field lines relate to field vectors? Okay, that's a really good question. That even if I did say it in the like that's important. So let me try to address it. The whole field line concept, the whole field line representation, the whole field line way of thinking is built from the concept of vectors. Like it starts with the idea of vectors, which I'll review in a second. We start in our mind with picturing fields as vectors. And then we realize that there's even a more efficient, more powerful way to picture fields. So we build the concept of lines from the concept of vectors. The vectors never become wrong. They're still like correct. And when in doubt, if you feel like you understand vectors, you can always go back and picture vectors. But lines ultimately are a way of capturing a lot more information, with fewer calculations and fewer drawings. So field lines are not the same thing as vector fields, but they're built from them. The best way to see that, the best way to see the relationship between the vectors and the field lines is to consider point sources. Okay, like I know I do this in the video, but I'm just gonna hopefully quickly remind you, like consider a point source like a proton sitting on a lab table or sitting somewhere in outer space, right? Like if you just have a proton, that is to say, a positive point source of charge. Right? If you have a positive point source of charge, then when we say it makes electrostatic field in the universe, or when we say that it contributes to the field of the universe, what we mean really is that a field is a vector valued function. So I'm starting with vectors here. Like it all does still, thank you. I appreciate it. What a field really is mathematically is a vector valued function, meaning that if you the input, the domain of the function is points in space, geographical locations, positions. That's the input of the function. And the output of the function is a force per charge, a vector, right, which indicates the number of newtons per each coulomb, that the number of, well, yes. I mean, so let me say that again. A field is a vector. I'm going to write it down. So what a field is what the field due to a point source is a mapping, a relation, a mathematical relation that says for any one location in space that you pick, I can tell you the vector that is sitting at that point in space. The vector that's sitting at that point in space has a magnitude and direction that represent how hard and in what direction a test charge, a positive 1 coulomb of test charge, would be pushed or pulled if it were sitting at that point in space, right? That's what a field is. So if we're picturing it in our mind, so a field is a bunch of vectors that are sitting there in space because some point source, some source of field, some creator of pushes or pulls waiting to happen is sitting there in space. So the vector field picture due to a positive point source would look something like this. Look like something like what I'm about to draw. And obviously this was in the videos, but would look something like this. And please, as usual, like stop me with any questions about this. This is what, right, that is the vector field. That's not field lines yet. That's a vector way of picturing what is happening to the universe due to some proton that's sitting in the universe, positive Q, right? Some amount of charge. It doesn't have to be one proton. It could be two, three. If a number of protons are jammed together in a tiny space, if you have a point source of 1 coulomb or 2 coulombs or 3 positive coulombs, then what we're saying is you pick any point. Oh, yeah, you pick any point in space at all. And wherever you pick, there's like there's a red vector whose tail is at the location you've picked. And the vector, if we were to draw this whole thing to scale, the vector is showing you how hard and in what direction a positive 1 coulomb of charge would get shoved if it were at that location of space, right? That's why we keep saying force per charge. These are forces waiting to happen. The force information is sitting there in each one of these points in space, whether or not an actual test charge is there. That's why we're calling this field, not just force, right? So, and notice the pattern. Like, again, I mean, if you watch the video, I think you've already, but notice the pattern. The idea is like, since there's a positive point source, and since field is always asking the question, what would a source do to a positive test charge? Like, we're always by convention assuming that the recipient of this force is positive, right? So positives push on other positives. So what this diagram is saying is anywhere you go in space, you're going to be pushed. If you were a positive chest charge, you'd be pushed away from that positive source. You'd be pushed by that positive source along a line connecting the two of you. You'd be pushed out along that radial line. And notice the arrows are getting smaller and smaller as we get farther away because it's inverse R squared law. We're saying the direction of each one of those arrows shows what would happen to a positive chest charge if located at one of the tails. And the size of the arrow is saying like that's how many newtons it would be pushed by. So the number of newtons is getting less and less as we get farther and farther away. Right? Like that's the first way we picture, and of course that's just a slice. That's like a cross section. It's just enough to show you the pattern. The idea is anywhere you go in space, there's a little red arrow sitting there representing how hard and in what direction you'd get shoved if you were a positive 1 Coulomb test charge at that location. Wait, let me stop for, let me stop for, just give me a show. Is that clear? So that's not field lines yet. That's the vector way of thinking about fields. It's a vector. This is technically a vector field diagram. Here, I'll write it. And it's not wrong. There's nothing wrong with it. It's just hard to draw. So this is the vector field diagram for a positive point source. Just give me a quick electronic hands if that so far is clear. Like, does that make sense to people? Thank you. That was fast. Thank you, Lila. Okay, that's good enough for me. That's one, two more. Okay, all right, awesome. Thank you all. And I'm not mentioning all my name because I can't even see them. But okay, great. Right now that's vectors. Now I'll even say because it already said in the video, I'm not going to draw again. And if I hope this is clear, if that source were negative. But everything else is the same, like negative Q instead of positive Q. All the arrows would look the same, except they'd all be pointing in. Yes, like if it's a negative point source, then all the arrows point in because no matter what, the field is always a discussion, a representation of what would happen to a positive receiver, a positive test, right? So positives push on positives, but negatives pull in on positives, right? I guess we discussed that with the example last. So if this were negative, all the arrows would be pointing in. Okay, that's vector. That's vectors. But you see, it's like very cumbersome to draw. And you got to remember, and I think we said this last time, like this is all this analysis is all about just points and all that. I don't even know if I got to say last Monday or the last time we met, we did a lot of math. We did a lot of computations just to figure out what the field would be, what the field vector would be at a certain point in space due to just 2 points of source charge, right? I'm sort of backing up here for a second, or sidebar. Last Monday, we did this long math problem. I mean, it was long. All the, right? I mean, cosines, sines, all this stuff. And all of what we were doing last Monday was just figuring out what the one vector sitting at a point in space, 0, 0, what the one vector would be to represent the field due to 2 dots of charge in the universe, just due to one positive dot and one negative dot. That was a lot of work for just 2 dots. And this picture is a complicated picture for just a dot. Where this whole ship is heading, what we want to be able to do is have our concept and our math for field. We want to apply it to things that are more realistic and more elaborate than just dots. I mean, if we had to do that much math to just add up the effects of 2 dots together, can you imagine how much math we'd have to do or how hard the picture would be to draw based on our current knowledge if we wanted to draw something realistic like a whole wire of charge? Imagine a whole line of charge that isn't just like 2 dots or 3 dots or four or even 100 dots. It's like a stream of continuous attached charge. That's what we ultimately want to analyze is like wires of charge or Van de Graaff generators, like spheres of charge or plates of charge known as capacitors. We don't want to just be sitting around just like looking at one proton all day. So we need a mathematical technique and we need a diagramming technique or representation that can handle more powerfully, like more than just a couple of dots at a time. Okay, so what we do is we move to this concept of field lines. We say, you know what? Okay, so the big point here, and again, I'm trying to bear in mind that you, of course, have already seen this, but I'm trying to. Vectors is a way to picture what's going on in space. For every point in space due to a source, there is a vector sitting there representing force, magnitude, and direction per charge. But now we say, okay, but look, what if we just connect up all those arrows into a line? Like, what if we do this? Or wait, tell me if you need me to go. Well, it says to simplify our drawing, it says to simplify our drawing and make our representation more powerful, more capable of managing more than a couple of points. Like, and I'll just say that again, if you're copying that, where we're trying to go with this is every all of our understanding is based on what each point of charge does to the universe, but we ultimately want to handle collections of points that are so closely collected together that they're not even countable anymore. We ultimately want to handle, maybe you can write this somehow in your notes and submit it for points. What we're trying to do is handle continuous distributions of charge. That's the goal here. Like the reason we're going to move from vector diagrams to field line diagrams, and the reason we're going to move from Coulomb's law, from the Q over R squared law to a flux law is because we're trying to handle continuous distributions of charge rather than discrete distributions of charge. Discrete means separatable, countable, like thingy, like dot, 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 dot. Continuous means whoosh, right? It's like the difference between like grains of sand and an ocean of water. Do you know what I mean? Like, so we're trying, everything we have so far helps us deal with quantized bits of charge. We want to handle non-quantized, like continuous, like infinitely um, um, divisible, infinitely divisible streams of charge. That's like how we experience it in the real world. That's where the ship is heading. So what we do, as it says here, is we connect the vectors into continuous lines. In other words, so stop me if you want to go back, but in other words, the field line diagram from a positive point source looks like this. Now that does not look very different, I know. But and again, this is I'm just talking about one point at a time here. The ultimate goal. Well, in fact, here, I'll skip. Okay, since you have seen the videos, this would be okay. This would be the field line. These are now field lines, not vectors anymore. Hard to see the difference in this picture, but I'm going to give you a couple more pictures to show you. This is the field line diagram from a positive point source. It's in contrast to this picture right here. I mean, the big difference is I sewed up all the vectors, right? I mean, or that's the big obvious difference, that I sewed up the vectors. Um, and that's what you do from now on. Field lines, they're not vectors, they're lines. Like one of the things that those rules were trying to tell you in the video last week is that well, yes, okay, I'm going to talk. I'm not going to write these things down now because I'm going to get myself bogged down again, and you already have them from the video before. But like, what's the difference between this picture in this picture? Like, what's going on? Well, okay, so they're both trying to tell you the same thing. They're both trying ultimately. They are both conveying the same information. What is that information? The information is magnitude and direction of force waiting to happen. Okay, either way, we're trying to capture a field. So we're trying to capture this idea that for any point in space you pick, somehow you look at the arrow that you landed on or that's nearest by you in the picture, and the arrow is supposed to tell you how hard and in what direction you would be shoved if you were a positive 1 coulomb of test charge, how hard and in what direction you'd be shoved due to that positive source that's at the center of the picture, right? Either way, the pictures are trying ultimately to tell you the same thing. But the difference is, the first big difference is that vectors tell you that with tips and tails. Here, despite what it might, here there's tips, but there aren't tips and tails in the same way. Let me be more specific. With vectors, the magnitude of a given, the length of a given vector arrow, the length of the vector arrow tells you the magnitude of the vector quantity. In this case, the size of the newtons per coulomb, like how many newtons per coulomb, right? Now here, we don't have that anymore. These things don't have length anymore. It looks like they have length. I mean, obviously there's like red marker on the page, but there's no length anymore. One of the rules, the thing that the rules are trying to tell you is these are now continuous rays. They go forever. Like, as the rules told you, the way you draw these rays is if there's positive source anywhere in your picture, yes, you start the ray at the positive source. And if there's negative source anywhere in the picture, yes, you end the ray at the negative source, right? But other than that, the rays go out forever or they come in forever. What do I like these right here? The tips of these arrows do not mean that these arrows have stopped at those tips. Those tips do not represent, those tips are there because that's the edge of the page. What you're supposed to understand about these lines, that the like rules in the video we're trying to say is that if they start somewhere, okay, it's going to be at a positive. And if they stop, no, let me put it a different way. If they start at all, it's got to be at a positive. If they end at all, it's got to be at a negative. If you, other than that, they're going on forever or they're coming in forever. So let me give you, I'm going to say more about that, but hold on. Say the source were negative. Then the lines, as I indicated before, would look like this. Or in fact, I'm going to give you a couple more quick examples now, as they did in the video. But like these are the field line diagrams from a positive point source and a negative, but let's start getting more elaborate. What if I had a dipole? Like what if I had something like this? Kind of like the problem that we solved um, last Monday. Then it would look something like this. And things are getting cut off because of the page here too, but um in fact, sorry, actually, that's hold on. Don't copy that yet. Wait, what did I just do? Hold on. I'm getting two things confused. Sorry. And I'm also going too fast, of course. Yeah, this is more what I mean to do. So you can copy that, and then if you need, I'm going to go to the next page. If you need me to go back again, I will. Let's do this one. I'll tell you the point I'm trying to make in a second. Say this would be two positive point charges, it would look more like this. This is the one I was accidentally drawing a second ago. Okay. Now, in fact, you know what? Wait, what time? Yeah, I'll stick with that for a second. Like, let's just, and I know you looked at a bunch in the videos before, but like, here's what I'm trying to say with these different examples. Like, here's a field line picture. Here's a field line picture. Here's a field line picture that's more elaborate and right. It's more elaborate. Here's a field line picture that's also elaborate. I'll try to break down why the pictures are what they are. But first, just notice in the pictures, notice these are not vectors anymore. They're not arrows. They don't have length as such. Like they look like they have, I mean, of course, you could measure them. They have length, but their length doesn't mean anything anymore. Their length, like the arrow at the center of this page, the horizontal arrow of this page in the center of this page, is as long as it is simply because it's starting at a positive and it's ending at a negative. And that happens to be a straight line. So that's the straight line distance between the positive and negative. But then there's like an arrow below it and an arrow above it. And each one of them is going from the positive and ending at the negative. And they're longer. right? Like the length just has to do with the fact. It's coincidence. It's just that we have this rule that says if a line is going to start, it's going to start at a positive. And if it's going to end, it's going to end at a negative. And that's it. Other than that, they have to come from infinity or go to infinity. What do I mean by come from infinity or go to infinity? I mean, like if you look any of the arrowheads that you see in this picture, and any of the tails, any arrowhead you see that is not slamming onto a negative, or any tail you see that is not like next to a positive, that means you're supposed to just read that as that's where I ran out of ink. Like that's where I got to the edge of the page. Like like right here, I'm gonna erase this. Like right here, this tail of this arrow right here, that's just a tail because I just stopped drawing, presumably at the border of the page. You're supposed to understand that that thing is coming in forever from infinity. Or similarly, this guy right here, it just stopped because I ran out of room on the page. It's going off to infinity. Furthermore, these things are curving. They're bending. So they are totally not vectors. I mean, they're built from vectors, but they're not vectors. What are they? Okay, they're trying to represent magnitude and direction in a more elegant, more simple, more powerful way. Direction, they're still indicating in the way that you kind of think, like whatever the arrowhead says, okay, that's the direction ultimately, but I'm going to be more specific about that in a minute. Magnitude is no longer being expressed by length of line. If there's any point that I'm trying to make for the last 7 minutes, it's that you no longer look at the length of one of these arrows to figure out the magnitude of field. What do you look at? You look at the density of lines in a particular area of the page, like literally how and again, I'm sort of intentionally not writing this down again because I'm going to rabbit hole and you've already written it down from the videos, hopefully. But I'm saying these field lines, they're meant to represent magnitude and direction just like vectors do, but they use a different method for representing that same information. Instead of using length to represent magnitude, instead of using length to convey newtons per coulomb, we're using density. So let's go back to the simplest case, like here, okay? None of these arrows has length anymore. They're just all going off to infinity. Sorry. So how can you tell by looking at this picture where the field is strong, where you'd be pushed hard, and where you'd be pushed weakly, right? Well, how you could tell is how close the lines are together. If you look at this picture, if you're near the center, of the cue, the lines are very dense. You have you have a high number of field lines per unit area on the page. So, and not only, right? And not only that, precisely so, if you picked any particular radius, like any distance from the positive cue, no matter where you went on that radius, as long as, like, in other words, if you're 2 centimeters from the positive cue dot, no matter which direction you went in, if I drew this, carefully, you'd always hit the same number of red lines per unit square centimeter, whether you're over here or you're over there, as long as you're like 2 centimeters from the white dot. But as you get farther and farther out, the lines are spread out. They are less dense per unit area as you get farther out. And they're less dense by a very specific, like, quantitative amount, right? Like if you went out 10 centimeters, if you went to a radius of 10 centimeters, you'd find all the arrows to be exactly as far from one another as each other, as they all are, right? So what we used to have in this picture, it's when you get to a certain radius, you see that all the arrows are a certain shortness. So that shows you the field is very weak, like way out here where the arrows are short, and the field is very strong way in here where the arrows are big. Now in our new picture, because we're trying to ultimately capture more elaborate situations with a simpler drawing, we're saying, forget length. Now it's about density. Now, wherever the lines are close together, the field is strong. And wherever the lines are far apart, the field is weak. And that's now the rule. So even when we get to complicated things like this picture, What we're literally saying is, or even better, this picture, right? We're saying like, if you go, well, which is, no, let's say this picture. I mean, either one, but let's say this picture, like if you went, if you go, if you look at a point like over here, the field is not nearly as strong as a point like over here or something. Like there's a lot more lines per unit area at point two than there is at point one. Do you see that? And that's indicating there's a lot stronger field. Like why? Because when you're in between the two charges, you're very close to one and you're very close to the other. So they're both reinforcing each other. Maybe they're fighting in terms of direction, but they're reinforcing each other in terms of magnitude. Whereas if you go all the way to point one over here, or you can imagine going even farther off the page to the right, you could get to a point where you're like not only really far from the plus Q, but you're even really far from the negative Q. And the farther away you're getting from both, the less dense the lines are going to be. I don't know if that's making any sense. Oh, wait. Oh, great. There's something in the chat. Hold on. Yeah. Right. Awesome, Abdul. Yes. And also thank you for the blessing. But yes, dead center would be the place where the magnitude of the field is the strongest of like everywhere in that picture. Yes, it does mean that. So good. I was gonna say something. So the density of so yes, and let me know if that makes sense. So one lesson I'm trying to say right now, again, it's a summary of the videos, but I'm trying to say that the way we read diagrams now is wherever lines are close together, that means strong field. And wherever lines are far apart, it means weak field. And it is that simple, by the way. I mean, it's hard to draw these pictures, but let's go backwards from the videos right now. Like, just try to understand how to read the pictures first. When you read the pictures, lines closer together means strong field. Lines farther apart means weak field. First of all, just raise your hand if that's clear. I mean, your electronic hand. Does that, like, density of field line? Thank you. Okay, awesome. Density of field lines indicates magnitude now. Great. Length of line no longer does. Okay, that's enough. Thank you. Let me get more specific because now this is in response. I'm about to start responding more specifically to some of the comments that you made like in the portal. So someone was saying they were all confused about, I spent all this time talking about scale and picking a scaling factor and all that in terms of drawing these diagrams. And yes, that can be confusing at first. It's like anything else. And once you get used to it, it's like actually, I'm using a lot of words, but it's a lot simpler than it sounds at first. What I'm getting at with all of this is like, I just like too quickly, like sketched out this picture. But if you could imagine that I was drawing it carefully, and if you can imagine I was drawing it carefully to scale, then really, the lines would be like, you could really rely on the fact that the lines would be very dense toward the center, like Abdul's question. And as you get farther and farther away from the line, from the charges, the lines would be getting very undense, very spread out. And in fact, let me be more like, not only, I think you can imagine if my diagram were more careful, the pattern that I'm describing would be more clear. But even more than that, it wouldn't just be sort of a intuitively clear pattern. It would be a quantitatively precise, quantitatively useful pattern. Like what I'm saying is, if once you sit down to draw field lines, if you like literally start by picking a scaling factor, if you say for every 1 coulomb, I mean, if you say, for example, for every 1 coulomb of charge, of source charge, I will draw 8 lines, kind of like that's what I'm doing here in a way. I'm saying, or here, I'm like say plus Q means like positive 1 coulomb of charge. I've just drawn 8 lines coming out of it. I picked 8 because it's just enough to really show you the pattern that they're going out radially in all directions. I mean, I hope you understand that's just like a cross section or like a represent, like there's really lines everywhere. But that's 8 I picked just to give you an idea of the pattern. 4 might have worked also, but I think 8 works a little better. 2 wouldn't really show you much, right? And I could have picked 16. but I picked 8. I just did this thing that said, all right, it's Q coulombs of charge. I'm drawing 8 lines, and then I draw them like symmetrically. Well, if I follow, once I make that decision, let's say I follow it consistently, no matter how elaborate the situation is. Like if I get to this kind of thing, let's say I tried to follow consistently, like with the, and I'm not even sure that I did. With the plus Q, if I drew 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, for whatever reason, I drew 14 lines coming out of the plus Q. Then what I should have done, and I'm not sure that I did, I should have then drawn 14 lines coming into the negative Q. If negative Q were negative 2Q, if it was meant to be twice as much charge, then I would draw 28 lines coming into it. This is what I mean by the scaling factor, because like at least 2 people asked about this actually. I'm saying that you decide on a number, and 14 is a stupid number. Like if I were being careful, not talking so fast, I probably would have just picked 8 or 16 or something, just enough to show you a pattern. But whatever number I pick, I got to be consistent with. And that means per amount of charge. So then if negative Q had happened to have been a negative 2Q, I would draw twice as many lines going into it as were coming out of the other one. And then I would connect them up in the simplest, smoothest way possible, right? Like I'm doing here. And if I did that, if I picked a scaling factor and then connected up the lines as simply and smoothly as I can, which means they're allowed to curve, they're allowed to bend, but they must always either go from positive to negative or positive to infinity or infinity to negative. Then if you follow the other rules and draw your picture, then what ends up happening is like you might see like you anyway, if you're really near the negative Q, you'd have twice as many lines in a given little region than you'd have when you were near the positive Q. And that would indicate that field is a lot stronger near the negative Q than near the positive Q, which it should be because the negative Q is a more intense charge, like a bigger charge. And so if you actually pick the scaling factor, then actually, literally, you don't just get a rough idea, but literally you could backwards calculate. Oh, yeah. Thank you. Yes, direct chat person. Very good point. I'm going to pause in 1 minute. You're absolutely right. He's reminding me, or someone's reminding me about the points that I want to give you. So yeah, I'm going to pause for a second and I'm going to actually ask you to let this sink in, to give you the points. But yeah, so the scaling factor idea is that once you just pick for each 1 coulomb of charge or each Q coulomb of charge, whatever, I'm drawing this number of lines, then what that means is at the end of the day, once you've drawn your picture according to all the other rules, then literally the number of lines per unit square centimeter on the page, like literally would translate to a number of newtons per coulomb, like all good scientific representations, like graphs, like vectors, like whatever. If you actually draw it carefully or have a computer generate it, then you literally can use it as a calculational tool. Is partly what I'm saying about the scaling factor. There's one other thing I was or 2 other quick things. So yes, I'm looking at the direct chat. It's sitting there, so I won't forget. And it's almost 4, and I do appreciate it. A couple other things, because this is also people ask. Like I keep saying the lines go off to infinity, or they hit a negative, or they come from a positive, or come in from infinity. If you're like me, or if you like what I was when I first learned that, that means nothing to you. It meant nothing to me. Okay, I know I keep saying it because it's true. But when they taught me, I still remember when I was an undergrad and they kept saying that. They're like, field lines start at positive or come in from infinity. Field lines end at negative or go out for infinity. They said it over and over. And each time, I don't know if you're consciously wondering this or unconsciously, but each time in my mind, I was like, as opposed to what? Like, what are you even saying? Like, yeah, I get like positive start at, I mean, I get that they start at positive, they end at negative, but then you throw in this infinity crap. Like, I thought I got it. And then you say the infinity thing. So that seems to cover everything. Like, what they were trying to say that I did not get, like, until I did, probably until I was teaching for like 15 years. What they were trying to say is that what field lines never do? What field lines never do is start or stop spontaneously in space. This is the key to field lines. That no, you'll never see the tail of a field line just sitting there in the middle of the page. And if you do, it means the person ran out of ink. It's just supposed to go on forever. Just follow the trend. And any tip that's sitting in the middle of the page, like this one right here, it's not sitting at the end. It's going off to infinity. That's what they're saying. They're saying field cannot be spontaneously started or stopped in space. The only thing that can create field is a positive source, and the only thing that can absorb a field line, so to speak, is a negative source. That's what they're trying to say. They don't start or stop spontaneously. So they're just showing a pattern that goes on forever. I am going to say one more thing, and then I am going to do I'll pause and do the points, because here's another question. So everything I've been saying so far, I don't know if it's helpful. It's probably not, but everything I'm saying so far is about how to understand the magnitude of these field lines. Like, again, see, what we're saying is they are arrows, but they're not vectors. They're these curvy, wavy things that were built from arrows, but that go on forever and show you magnitude not by their length, but by their density. Okay, that's what I'm saying so far. I'm saying these arrows show magnitude by how close together they are. That's it. They don't show magnitude by how long they are. How long they are, it doesn't mean anything. They're infinitely long, in effect. Okay, that's magnitude. Before I give you the points, before I pause and give you the points, let me say something about direction. Because in the videos, I say a lot, or I tend to say a lot about tangent lines. And the tangent line, at least two people wrote me like, oh God, tangent lines. Like, wait, what? The what? Like, I don't like tangent lines. That's confusing. Like, okay, I hear you. Here's what I mean about tangent lines. I'm saying that, again, the orientation of these arrows, like yes, there's still a reason that we're still drawing tips. Although, quite frankly, once you really get used to these field lines, to be honest, it really gets easier to draw the tips. And you'll see this in all if you go to Google Images and all that, their field line pictures tend not to have the arrows at the end. I mean, you could do it either way. And sometimes I forget, like I did here, like they tend to put their arrows right in the middle of the lines like this. That's totally valid. And some pictures will make a lot. Like you can make a lot of them if that helps. In other words, where we put the tips, in fact, maybe that is the best thing, especially when you're learning it. I could put these tips like everywhere through the lines. That's really what I should do. I don't know why I never did this before. You could put the tips everywhere, or you could just put like one right in the middle, as Google Images tends to do. I mean, it's not Google Images, you know what I'm saying. You can do it like that. And that tends to get at the idea that I'm trying to say, which is, yes, like, first of all, the tip is not an end. It's not an end. It's just a tip showing direction. But if you get used to the idea that you could put those tips anywhere and everywhere, then you start seeing what I'm saying about tangent lines, which is this. It's the direction of the field line at a given point that indicates the direction a test charge would be shoved if the test charge found itself at that given point. So in other words, this is where the tangent thing comes in. Like, say there was a test charge, lowercase q, right here at that, right there in space. Then what the red field line is trying to say is right there at that point in space. You could picture right there's a vector. There's a vector pointing along the tangent to the curve. What is a tangent line? A tangent line is a line that intersects a curve at only one point. That's what a tangent is. Not at two. It doesn't cross a curve. It grazes a curve, right? That's what a tangent line is. And that's why we use them for derivatives, because derivatives are about the rate of change, the slope of a curve at one point. So a tangent line is just like a way of saying, like the tangent to this curve is a way of picturing in our mind the steepness of the curve at that point. So we're saying if there was a little q at that point, it'd be shoved like up. Whereas if it were like at this little point here, it'd be shoved down. right? That's why the field line can curve, because it's saying like if you're over here, you get shoved one way. If you're over there, you get shoved a different way, right? We're showing the pattern of like of where you get shoved. But it's like one line because wherever you are on that line, probably the magnitude of your shove would be the same, but your direction would be different, right? So that line, what it is, go back to the original of all this, the line is a sewing up of a bunch of vectors. We're saying that that line is a bunch of vectors that all got connected together. So everywhere you are on that line, you can imagine a little vector, a tangent to the line that would show you which direction you would get pushed or pulled if you were a positive 1 coulomb of test charge. So the tangent line is just a way of saying whatever the curve is doing at that point, that's the direction of the field. And however dense the curves, the curved lines are at that point, that's the magnitude of the field. So we are trying to convey the same information as before, but in a more elegant picture. Last, I'm going to make you a compromise. You know what's going to happen? As a compromise for your indulgence, in a minute, I'm going to make this one more point. Then I'm going to make sure you get your points. And then we're going to end early, a little bit, like not hugely early, obviously, but a little bit early, just because there's no point in me starting anything new or anything. So as a reward for your indulgence, just well, not that early. Whoever just left, really? I mean, really? Can we talk about that person now? No, we can't because I don't know who it was. And because that would be rude. Okay, so the last thing I want to say, because someone asked about this too, like why do the field lines not cross? Like, right, that was one of the rules. Like field lines can bend, they can curve, they have to start at positives or come in from infinity, they end at negatives or they go off to infinity. They're all built from a scaling factor. That was pretty much all the rules. And then and then given all of those rules, you draw the field lines so that they are the simplest, smoothest activation of all of those rules you can do. It takes a little getting used to, but that's what the field line picture is. So why can they never cross? Why can they never cross? Because, in effect, what I just said, that the field line is the sum of a bunch of vectors. That's what the field lines are. They are the result of, like, what these field lines in this picture is. Hold on. Oh, wait. Was it him who left? Okay. What the field line picture, what this really is, if you turn this on its side, which I don't think I can do, if you like turned your head and looked at it, or you tilted this picture, well, and especially if you made one of the charges a little stronger than the other, so you made one of the set of lines more dense than the other, that would be in effect the picture, the field line picture from the homework problem that we went over last Monday, right? Like, because we had a positive point source and we had a negative point source in that homework. Now, they weren't equal, but they were opposite, right? And they were like over here, like, so you'd have to tilt your head a little bit. But in other words, what these field lines are is the result of going to every point in space and taking the vectors from one and adding going to every point in space and taking the vector from one and the vector from the other and adding it together and getting a new vector and then sewing up all of those new vectors that we got. Like, that's what this is. And this is why we're doing this. Because again, let me remind you, you had to work very hard, and so did I, last Monday, just to add up two vectors at one point in space. Can you imagine how much work we'd have to do if we had three vectors, like 3 point sources, or if we wanted to do that calculation was just the sum of two vectors at one point in space. I want to know, like, what's going on in a lot of points in space. So what this is our pictorial, our graphical representation of what would happen if we had gone to every point in space, added up the vector from the positive q and the vector from the negative q, like added them together, got a new vector at every point in space, and then sewed up all those new vectors. They'd be creating these curved, smooth lines like this. These curved lines are the net result of adding up all the vector contributions from all the sources creating the situation. Therefore, this is already the net result. Like, so therefore, there's no more adding or crossing that can be done. The reason two field lines can't cross is that field lines are what happens when you've already crossed all the vectors and come up with new vectors. I don't know if that makes sense or not, but they can't cross because there's nothing for them to cross with. They are the outcome of adding together vectors. I don't know if that makes sense or not. So I'm going to do now, just tell me. Well, I'm going to give you, I'm going to stop. I want to give you points now, and then like bear with me, and then you're going to go. But just indulge, just raise your electronic. Did this help at all? Does this clarify anything? I mean, you could be polite. I mean, you can be. But that's a yes. All right, I'll take one yes. Is good. Okay, that's a lot. All right, that's cool. Thank you. I mean, it's a loaded question. What are you going to say? No. But oh, cool. Oh, very good, Abdul. Oh, Abdul's a rock. That's great. And yes, that's very. I think I know that one. I mean, I'm not sure then, but that field line simulators are great. And yes, they're and maybe you're using the lab. Anyway, that's great, Abdul. Thank you. You've been on fire today. So bear with me for a second. I'm going to give you the points for the. I'm not giving you feedback. Hopefully, this class was kind of the field. But if you still have questions, any comment that you made about the video where you're still confused, then tell me that next time we have class. Like, because we're not behind, by the way. I mean, I'm behind on your work, but we are not behind in the curriculum. So there is time for you to still get this straight next week when we meet. So I apologize if I didn't answer one of your comments about the videos, then just tell me next week when we meet. Hold on. So I'm going to do this right now. So bear with me for a second. Yeah. Okay, here we go. Right. So as long as you I'm just looking, as long as you did resubmit it and you gave me these comments, I'm looking right now. So again, I'm not, so I've read them. I'm some of them are so, oh my God, some of you guys even included diagrams. That's amazing. No, these are so thorough. So please tell me Monday or whatever we next, if I still haven't clarified this sufficiently, then just tell me the question in class. But those are the points for that. Now hold on, it's 4:12. I still am going to let you go a little. Bear with me for a second more. And obviously, I still do have your exams, and you're being very patient about that. Oh, the other thing, I'm going to put this in the chat too. I said this to the other classes. If you, sorry. Very helpful. Thanks. Okay. Oh, cool. Thank you, Nico. Okay. I'm putting this again in the chat for a specific reason. I'll tell you why in a minute. Like that's my cell phone, right? To encourage you to text me. I'll tell you specifically why in 1 second. So you're going to go like 5 minutes early. It's not going to be hugely early, but still be early. Because I know you still don't have your midterms. If you're starting to get anxious about your grade in this class, I can well understand that. I can't just automatically I'm hopefully going to use the holiday to catch up, although that I will be with family stuff, so it'll be whatever. Hopefully you'll have that information soon. But if you're just a person, if it's what I'm trying to say is if you want to text me to set up like a 15-minute phone appointment just to talk about your general standing in the class, even if I am not in the car and I can be looking at your exam while we're talking, I can do that even if I can't give you an exact number. Sorry, I'm getting confused. What is this? Right. Even if I, so maybe I can look at your exam roughly and give you a rough idea or even if I can't be specifically looking at your exam. Like I know you, most of you, and your work maybe better than you think at this point. And so if you're concerned about your grade and it's freaking you out that you still don't have a midterm yet, and also it is true, like my grading system is just elaborate enough that you can't tell from Google Classroom like what your average is right now. Like I know that. So if it's freaking you out and you just want to talk for 15 minutes on the phone, so I could say to you personally what your situation seems to be and where you're heading and what's going on or what you would need on the this to, I'm happy to do that. So just text me and we'll set up an appointment. And again, I might still be missing information, but at least I can look at the rest of your situation and tell you like what I really think is going on. Okay. We're almost done. It's 4:15. I think I'm gonna let you go. Hold on one second. And I'm not looking at the Zoom right now because I'm just looking at these numbers. Yeah. Okay. So I'm looking at this. So that's myself. So, okay. So thank you for bearing with me on all this. Hopefully that was sort of helpful, whatever. So you don't have class Wednesday. So just you keep catching up with whatever you need to catch up on. There's nothing new in this class yet. And I'll hopefully catch up with what I need to catch up with you and have a and I'm here if you want any questions right now to ask. But other than that, the recording is stopping and have a great holiday, everybody.